Section 5.1, Laws of Exponents. An exponent, or power, is a number that indicates how many times another number, called the base, is used as a factor. For example, 3 raised to the 4th power, 3 with an exponent of 4, means that you write down 3, that's the base, 4 times. So you write down 3 4 times, you multiply them together, you get 81. In general, if a is a positive integer, the expression x to the a power means you write down a factors of x and multiply them together. A indicates that there are a factors of x. For any real number, x to the first power just means x, because you write it down one time, and that's the answer. An exponent of 0. For any non-zero real number, x to the 0 power equals 1, and we'll talk about that more later. Why is x to the 0 power equal to 1? So let's work through some example problems here. So we're going to simplify. 7 to the first power means you write down 7 one time. You don't really have anything to multiply it by, so you're through. That's it. 7 to the first power means just 7. All right, let's move over and do negative 2/3 to the 5th power. When you're raising something that's in parentheses to a power, I like to write it down, parentheses and all. So it's negative 2/3. We need to write this down 5 times because it's raised to the 5th power. So we're going to write down negative 2/3 5 times, and then think about what our answer will be. When we multiply these first two negative numbers together, a negative times a negative will give us a positive. When we multiply these two negative numbers together, once again, negative times a negative will give us a positive. That leaves us one negative sign at the very end that's going to make our answer negative. What is our answer? What is 2 times 2? That's 4. Times 2 is 8. Times 2 is 16. Times 2 is 32. That's our numerator. Our denominator is 3 times 3 is 9. Times 3 is 27. Times 3 is 81. Times 3 is 243. So our answer is negative 32 over 243. Negative b to the first power. Raising something to the first power doesn't change it. It's just negative b. You can use those parentheses or not. It doesn't matter. Negative b to the 4th power. Notice that negative b is in parentheses, and when something is in parentheses, I like to write it down 4 times, parentheses and all. Think about our negative times a negative is a positive. Those will cancel each other out. Negative times a negative is a positive. Those will cancel each other out. So I just have b to the 4th. Negative 7 squared. Let's back up so we can think about this a little bit. Notice when we had negative 2/3 to the 5th power, an odd number, we got a negative answer. When we had negative b to the 1st power, an odd power, we got a negative answer. When we raised negative b to the 4th power, an even power, we got a positive number. Is that a pattern that we're always going to see? And notice that these 3 previous examples have all had parentheses around the negative and the base. The negative sign was a part of the base. Negative 7 squared is different. There are no parentheses. So the question is, what are we squaring? Well, you're squaring just the 7. The negative sign is out front, waiting to make your answer negative. It is not being squared because the exponent applies only to what is to its immediate left, unless you have parentheses to tell you otherwise. That, too, means you're squaring only the 7, not the negative. If you had wanted the negative to be a part of the base, you would have had to use parentheses to make that happen. If you have 8 to the 0, anything to the 0 power is just 1, and we're going to discuss why that is later. Negative 10 to the 0 power. Negative anything to the 0 power is 1, and notice that the negative is a part of the base, so our answer is 1. What about 5 times x to the 0? What's being raised to the 0 power? Just the x. So x to the 0 is 1, but there is still a 5 out front waiting to multiply times whatever the result of the exponent in the base is. So it's 5 times 1 gives you 5. Only the x is being raised to the 0 power because we don't have parentheses to tell us that the 5 is a part of the base. Negative y to the 0, we have a negative out front. It's not part of the base. It's out front waiting to make our answer negative, and y to the 0 is 1, so our answer is negative 1. Let's look at some laws of exponents. We begin with x to the third times x to the fourth. Raising x to the third power means we write it down 3 times. We want to multiply that by x to the fourth, so we write down x 4 times. How many x's are there? 7. It's x to the third times x to the fourth. Could we just add those exponents? Does that work every time? Yes, that does work every time. In fact, we have a product rule for exponents that tells us that for any non-zero real numbers, x, and for any positive integers, a and b, then x to the a times x to the b equals x to the a plus b. If you're multiplying and the bases are the same, you can add the exponents. 2 to the third times 2 squared is 2 to the 3 plus 2. Add the exponents. The bases are the same. We can add the exponents. 2 to the fifth. Negative 3 to the fourth times negative 3 to the eighth is negative 3 to the 4 plus 8. That's negative 3 to the 12th. And what happens when we take a negative number and raise it to an even power? It gives us a positive answer because there are an even number of negative signs that will all cancel each other out. So we can simplify that to 3 to the 12th. A to the 8th times a to the 13th is a to the 8 plus 13, and that gives you a to the 21st power. This first problem has a problem. Let's rewrite that. It should be b to the 10th times b. Second b should not be a part of the exponent. So if you have b to the 10th times b, we know that our law of exponents says that we can add the exponents. So we have 10 plus, but the second b doesn't have an exponent. If it doesn't have an exponent, what do we always know that it is? 1. So that's b to the 10th plus 1, which is b to the 11th. So if a variable doesn't have an exponent, we can always assume that it is 1. Our second example, we have y. We're multiplying all these y's together. They all have exponents, so we're just going to add those exponents. 4 plus 5 plus 2 plus 7. We can extend our power rule to include 4 bases multiplied together, as long as they're all the same. 4 plus 5 is 9. 2 plus 7 is 9, so we get y to the 18th. X to the third times x to the fourth. The x to the fourth has parentheses around it. Does that do anything special? No, it just means you're multiplying. So we have x to the third plus 4. That gives us x to the 7th. What about x cubed, y to the 5th, x to the 4th, y to the 9th? We can only use our law if we have the same base. This is all multiplication, and we know that when you're multiplying, the order in which you multiply doesn't matter. So just for my peace of mind here, I want to rewrite this as x to the 3rd times x to the 4th times y to the 5th times y to the 9th. I don't really have to do that, but I just wanted to. So now that we've changed the order of the multiplication, we'll get the same answer, but it makes it more easy to realize that we're going to use our addition rule. So we'll make it x to the 3 plus 4, y to the 5 plus 9. That gives us x to the 7th, y to the 14th. And we cannot combine those because their bases are different. The product rule only works when the bases are the same. So our final example here is x to the 6th over x squared. That's not a product, that's a quotient. So we're going to have to just think what this means. X to the 6th, we write down 6 x's. X squared, we write down 2. Now any number over itself is 1. So this x over this x is 1. This x over this x is actually 1. So we can actually cancel all those x's, and we will be left with how many x's? We have 4 of them now. Notice that x to the 6th over x squared, if you subtract 6 minus 2, you get 4. So is that always true? If you have a quotient and the bases are the same, can you subtract the exponents? Yes. X to the a over x to the b equals x to the a minus b. So when you're dividing, if the bases are the same, you can subtract the exponents. 5 to the 7th, 5 to the 4th is 5 to the 7 minus 4, 5 to the 3rd power. Negative 4 to the 11th power. Let's write that as a fraction. Negative 4 to the 11th power, that's in parentheses, over negative 4 to the 9th power. So the bases are the same, so we can write that as negative 4 to the 11 minus 9, and 11 minus 9 is 2. So it's negative 4 squared. And what happens when you raise a negative number to an even power? The negative signs will cancel and your answer will be positive. So we can simplify that to 4 squared. X to the 4th over x. The x in the denominator doesn't seem to have an exponent. Can we make one? Yeah, it's just 1. So that's x to the 4 minus 1, which is x to the 3rd power. Our next example has both a and b in it, in the numerator and denominator. So we're really going to kind of consider the a part separately than the b part. And if I can read them, I'll still be able to do this problem. So that will be a to the 8 minus 3 times b to the 12 minus 7. That's a to the 5th, b to the 5th. And that's our answer. A to the 5th, b to the 5th. So now, finally, let's use that rule that if we're dividing and the bases are the same, we can subtract the exponents. So let's look at this first example. 2 to the 3rd over 2 to the 3rd is 8 over 8. That's 1. But using our rule of dividing, our quotient rule for exponents, we're dividing and the bases are the same. We get 2 to the 3rd over 2 to the 3rd is 2 to the 3 minus 3. That's 2 to the 0. We already simplified this problem one way and got 1. We want consistency in mathematics, so if we solve it this other way, we also need to get 1. So we have to define 2 to the 0 as 1. So x to the third over x to the fifth, we can write that x to the third as 3x's, x times x times x. X to the fifth, x times x times x times x times x. So we can cancel x over x is 1, x over x is 1, and x over x is 1. We'll be left with x times x in the denominator, so that's 1 over x squared. X to the third over x to the fifth. Using our quotient rule, we take 3 minus 5, we get negative 2. Once again, we have worked the problem in 2 different ways. And in order to be consistent, we need to define 1 over x squared as x to the negative 2. Negative exponents indicate location. So, if we have x to the negative a, we're in the wrong location. We're currently x to the negative a is like a fraction. It's in the numerator. It's in the wrong location. We have to take it down to the denominator, and we have 1 over x to the positive a. What about x to the negative a? 1 over x to the negative a. It's in the denominator. It's in the wrong location. So we have to move it up to the numerator, and it becomes a positive a. When you put your base in the correct location, the exponent will be positive. 2 to the negative 3, that's like 2 to the negative 3 over 1. A negative exponent indicates location. It's in the numerator, it doesn't belong there. We have to take it to the denominator. What goes in the numerator now? A 1. You have to have something there, and just like if you have to write 2 to the negative 3 as a fraction, you put it over 1. Once you take it to the denominator, if you have to put something in the numerator, you put a 1. Negative 6 to the negative 2. It's in the numerator, it's in the wrong location, so we take it to the denominator. Negative 6, it then becomes a positive 2. Once you put it in the correct location, the exponent is happy, so it's positive. If you're raising a negative number to an even power, that gives you a positive answer. So we can simplify that further as 1 over 6 squared. Y to the negative 6, it's in the wrong location. Take it to the denominator. It's happy, it's positive. Negative 2w to the negative 1 power. Now we have 2 negative signs here. We have a large negative sign that's in front of the 2w. It is large negative signs like this one that are down front indicate value. It's trying to make your answer negative. We have a small negative sign that's up high with that 1. It is part of the exponent. It indicates location. One of the most common mistakes that students make is they want to cancel these 2 negative signs. But I like to say they're in different places. One's down low, it's big. One's up high, it's little. They're different sizes. They're in different places. They cannot cancel each other. They can't communicate with each other. They mean different things. And so you cannot use one to cancel the other. So what can we do then? Well, the negative exponent, negative 1, indicates that that 2w is in the wrong location. We bring the 2w to the denominator. It now is raised to a positive 1 exponent, which doesn't really do anything. So we're through with the exponent part. But this negative out front is still there. It's still there, making our answer negative. Another example, negative 3 to the negative 4. The negative in front of the 3 is there, waiting to make your answer negative. The negative 4 is telling you that that 3 is in the wrong location. It's got to go down to the denominator, where it will be to the positive 4 power. Let's make that a little smaller so it's obvious that it's an exponent. So that 4, that even exponent, does not apply to the negative, just to the 3. If we wanted that negative out front to be part of the base, we would have to use parentheses. We didn't, so only 3 is being raised to the negative 4th and then the 4th power. What about 10x to the negative 4? The 10 is happy where it is. That negative 4 exponent does not apply to that 10. If we had wanted it to apply to the 10, we would have had to have used parentheses. So the 10 is happy. The x to the negative 4 is not. We have to take it to the denominator, where it will become a positive 4, and that's our answer. Negative 7 to the negative 2. The negative is out front, ready to make our answer negative. The 7 is not happy where it is. It has to go to the denominator, where it will then be raised to the 2nd power. We need something for the numerator. We put a 1 there. So it's negative 1 over 7 squared. Negative x, oh, it's in parentheses to the negative 6. So this time the negative comes down with the x, where we raise it to the 6th power. What happens when you raise a negative number to an even power? All the negatives cancel each other out, and you get a positive answer. X to the negative 3, y to the 5th. The y is perfectly happy where it is. It's in the numerator. The x is not. Take it to the denominator, and then it will become happy too. Once you get the base to the right location, the exponent is positive. Mn to the negative 2. Leave the m alone, but the n has to move to the denominator. 1 over a to the negative 5. That a is not happy where it is. It's in the denominator. We have to move it to the numerator, where it will have a positive 5 exponent. We don't really need that 1 anymore. We move the a up to the numerator, so we're fine. The 3 is happy. The y to the 3rd is happy. They have positive exponents, but x to the negative 1 is in the wrong location. Take it to the denominator, where it becomes x to the positive 1, which you can write if you want to, but you don't have to. Either way is fine. What about 4 over x to the negative 2? That x to the negative 2 is in the denominator. It doesn't belong there. We need to take it to the numerator, where it'll have a positive 2 power, so it's 4 times x squared. Write as an expression using only positive exponents. So 3 to the negative 4 times 3 to the 2nd power, we have a product, so we want to use our product rule. We'll add the exponents. 3 to the negative 4 plus 2. That's 3 to the negative 2, but we cannot use negative exponents in our final answer. 3 to the negative 2 is 1 over 3 squared. A to the negative 5 times a to the negative 2 is a to the negative 5 plus negative 2. That's a to the negative 7, but our final answer can only have positive exponents, so it's 1 over a to the 7th. Let's circle our answers here. B to the 10th power times b to the negative 3rd times b to the negative 4. Our product rule tells us that we can add all those exponents. So that's b to the 3rd power, and that's it. X to the 5th over x to the negative 3. Our quotient rule tells us that we subtract those exponents. Be careful, because it's 5 minus a negative 3. That's x to the 5 plus 3. And our final answer is x to the 8th. M to the negative 4 times m squared. We can subtract those exponents. Negative 4 minus 2, negative 6, 1 over m to the 6th. Y to the negative 8, we can subtract minus a negative 11. Y to the negative 8 plus 11. Y to the 3rd power. So in terms of application problems, what kind of application problems do we have? Physicists study different kinds of electromagnetic waves. An electromagnetic spectrum shows the relationship between the wavelengths of these waves. Consider an infrared ray whose length is 10 to the negative 4 meters, and an ultraviolet ray whose wavelength is 10 to the negative 8 meters. Which of these rays have the greater length? So we're comparing 10 to the negative 4 to 10 to the negative 8. I don't really have a sense of which one is larger when they're written with negative exponents. What if we change them to fractions? That's 1 over 10 to the 4th, and that's 1 over 10 to the 8th. Which one is larger? In general, when you're comparing fractions, what's larger, 1/2 or 1/4? 1/2 is larger because the denominator is smaller. You've only divided 1 into 2 pieces versus 4 pieces. So 1/2 is larger. So what's larger, 1 over 10 to the 4th or 1 over 10 to the 8th? We know that a smaller exponent means a larger fraction when the numerators are the same. So 1 over 10 to the 4th is larger. What is the ratio of the longer to the shorter wavelength? So longer to shorter, we know that 10 to the negative 4 is longer, 10 to the negative 8 is shorter. We want to know what this ratio is. We can use our quotient rule, 10 to the negative 4 minus a negative 8. So that's 10 to the negative 4 plus 8. So that's 10 to the 4th. That's the ratio of the longer to the shorter. If the length of a side of a square is tripled, is the area of the square tripled? The length of a side. So we have our original square, which is just x. We don't know what it is. And then we're going to triple the length of the side. So each side will then be 3x. How do you find the area of a square? X squared. You just take the side and you square it. How do we find the area of this square? 3x squared. In this case, we're squaring both the 3 and the x. So we have 3x times 3x, 9x squared. So if you triple the length of the side, what happens to the area? It's not tripled, it's 9 times as big. Triple the side, 9 times the area. On day 1 of a 7-day cruise, 3 people were sick with swine flu. Each day thereafter, the number of sick people doubled. I really enjoy cruises, but I don't know, I'm rethinking them. How many people were sick on the 3rd day of the cruise? On the 6th day? On day 1 of the 7-day cruise, 3 people were sick. Day 1, 3 people were sick. Each day thereafter, the number of sick people doubled. Day 2, 6 people were sick. Day 3, 12 people were sick. Day 4, 24 people were sick. Day 5, 48 people were sick. Day 6, 96 people were sick. Is there another way we can do this? Day 2 is 6. So what we did is we took 3 times 2. Day 3, we have 12 people sick. So we took the previous day, which was 6, and multiplied it times 2. So we had 3 times 2 times 2, or 3 times 2 squared. Every day that we go out, we want to multiply it by 2 another time. 3 times 2 to the third. 3 times 2 to the fourth. 3 times 2 to the fifth. How many times as great was the number of people sick on the 7th day as compared to the number of people sick on the 3rd day? Oh, so we have to do day 7 now. Day 7, we know we can just double that 96. That'll be 192. Or we could, using our pattern that we've developed, realize that that one's going to be 3 times 2 to the 6th. So how many times as great was the number of people sick on the 7th day as compared to the number of people sick on the 3rd day? So the 7th day is 3 times 2 to the 6th. The 3rd day is 3 times 2 squared. The 3's cancel, and we have 2 to the 6 minus 2, or 2 to the 4th. How many times greater, or how many times greater is the number of people on day 7 versus day 3? 2 to the 4th. If we had to work out how many people were sick on day 152, we really need to recognize a pattern and be able to calculate larger numbers without having to do all the ones in between. So for these numbers, it was pretty easy to just say the answer was 3, 6, 12, 24, 48, 96, 192. But if we had to go out to day 200, say that boat couldn't come into port and it had to stay out there on the ship or on the water, we need a pattern. The value of an antique motorcycle T years after it is purchased is given by the expression 9,000 times 1.2 to the T power. Evaluate the expression for T equals 0 and explain the significance of this value. So 9,000 times 1.2 to the 0 power. Anything to the 0 power is just 1. So that's 9,000 times 1, which is just 9,000. T is 0, T is time. Time is 0. That means you just bought the motorcycle. Explain the significance of $9,000. That's how much you paid for it. You paid $9,000, or that's how much it was worth. What is the value of the motorcycle 3 years after it's purchased? Usually the value of something goes down after you purchase it, but this is an antique motorcycle, and we're multiplying times 1.2 every year. So if we have 9,000 times 1.2 to the 3rd power, we can calculate that. Now it's worth $15,552. This is an antique motorcycle. It gets worth more It's worth more every year. So is currently, after 3 years, going to be worth $15,552. That's all for this section.